Okay. Okay, let's get started. So we're going to finish emerging memory technologies, and then we're going to start with quality of service and interference, a completely different topic. So let's see if we can finish the emerging memory technologies in the next 9 minutes, because I don't have much left. There's a lot of other topics, of course, like how do you design data structures to take advantage of persistent memory, but we're not going to get into those issues. But I'll talk about one issue actually in persistent memory, especially in a single-level store. How do you ensure consistency of system and data if all of your memory is persistent? Actually, this is part of a bigger question. How do you design the operating systems with completely persistent memory? That's interesting too. So I think there are two extremes in the answer to this question. Basically, programmer transparent, meaning that let the system handle it. Programmer has no control or no burden. And the second is programmer only, let the programmer handle it without any system support. And there are many alternatives in between also that I'm not going to cover. I'm going to cover the programmer transparent solution because this could be useful for enabling a persistent memory system. So what is the problem? This is also called crash consistency. Let's assume that you're adding a node to a linked list that's persistent. What you need to do is, if you want to add the node, you first link to the next one, and then link to the previous one, and then you have a consistent data structure at the end. What happens if, while you're doing the operation, system crashes? What do you need to do? Basically, you can get to an inconsistent state. You may never get linked over here, or you may actually have multiple links over here. Who knows, right? And system crash can result in inconsistent memory state, basically. Especially when you're removing a node, that also happens, right? What are the current solutions? Current solutions usually add burden on the programmer. So your program needs to change, first of all, which means that what happens to legacy programs? If you have a legacy program that's running on a system that's not persistent, how do you handle that? I think that's one problem. And the second issue is this adds programmer burden. Basically what happens is usually existing solutions are some sort of atomicity based. You basically have a transaction that begins and transaction that ends. And if the system crashes somewhere in the middle, it appears as if the transaction has never begun, basically. So it's very similar to transactional memory, except it's done for persistence here. And we thought this would actually limit the adoption of MEM because you have to rewrite the code with clear partition between volatile and non-volatile data. There's a lot of burden on the programmers. And there's example code. You update a node in a persistent hash table. It's very ugly, sorry, but you can see some things. Basically, you need to make it transactional, and you need to declare the arguments, and you need to basically make all of the functions transactional. So you need to manually declare the persistent components, and you may need a new implementation for some functions to ensure that they satisfy persistence. And if there's a third-party code, you need to ensure that that's also satisfy the requirements, right? But that's not necessarily true. Whenever you change an entire system, you don't actually always use the libraries from, and there might be prohibited operations also, right? Direct assignments may not be good. So there's a lot of burden on the programmers that are caused because of persistence. So we wanted to have an approach that's completely programmer transparent. So let's say really extreme. But I think it's important to examine the extremes if you want to get to a point that is not necessarily extreme. So basically, this approach is transparent hybrid non-volatile memory. There are many ideas inside there, but I'll give you the very high-level key ideas. It's actually a hybrid memory. The goal is to have software transparent crash consistency in persistent memory systems. And the key idea is very simple, actually. The system periodically checkpoints its state. And if there's a crash, it recovers to a previous consistent checkpoint on that crash. And then now you can start at that point that's really consistent. That's the idea. It's a hardware-based checkpointing mechanism, which means that there's a lot of nitty-gritty that you really need to deal with in the system to ensure that you checkpoint everything. If you miss something, then this doesn't work, right? You really need to checkpoint your entire system state. And I'm not going to go over this in detail. I just want to give you the basic idea. Basically, there are multiple granularities that you exploit to reduce both checkpointing latency and metadata overhead. And you need to, if you have a checkpointing mechanism, you cannot just checkpoint. And while you're checkpointing, you cannot afford not keeping on executing. Basically, while you're checkpointing, you should be executing, which means that you actually need multiple copies of the data somehow, because you cannot execute on the thing that you're not checkpointed. So you need to have buffering, additional buffering. So basically, it adapts to DRAM and NVM characteristics also. But again, I'm not going to go over this in detail. It's very interesting, I think. And the performance is very interesting because it's hybrid memory, because it takes advantage of DRAM. It actually gets very close to the performance of idealized DRAM with zero cost consistency. And we actually released the source code. You can actually try it on if you have the stamina to work with a Gem 5. The source code is out there. So basically, overlapping checkpoint and execution, this is the simplest concept. You can run checkpoint, run checkpoint. Basically, you have two epochs. At the end of this epoch, you need to store the data that you modified in this epoch. And when you actually overwrite that data in this epoch, you cannot get rid of it because you may actually go back to the end of this epoch if you have a crash over here, right? So you actually get rid of the data that you overwrote over here only after this epoch ends. But this is not a good solution because you run checkpoint. Ideally, you would like to do this. You run while you're checkpointing, you keep running. While you're checkpointing this epoch, you keep running. And you always overlap checkpointing and running, which means that now you have more requirements. There are multiple copies of data that you need to keep. It's not just this epoch and this epoch, but it's actually 3 epochs of data. So you need to have multiple copies of versions of data. And that management becomes complex. It's not that easy. But that's all I want to say about this. It's not an easy problem. You can punt on the software to do this completely, or you can have the hardware to do this. But there's a lot of solution space in between that's not very well explored at this point. Yes?
Just a question about the question.
Okay.
The problem you're addressing, is it because not all the memory is persistent?
No, it's...
Or unrelated to persistent, not persistent? Transactional. You're looking at checkpointing. The program takes something, blows up.
Basically, the problem happens because you manipulated some data structure, right? And the system crashed.
What is this crash? What is the nature of crash?
So the nature of the crash, maybe your power failed completely. Right?
Okay, had all the memory been persistent, usually crashes between registers.
Yes. Okay. All the memory. Now I understand. Yes.
Still need to do this? Yes.
Yes. Basically. Yeah.
So it's unrelated to persistent, not persistent. It's just addressing the crash resilience.
That could be true, but if you... so I'm trying to understand your question fully. If all your memory had been persistent, meaning all of your registers and everything, right? Mm-hmm.
Still write this paper, or would this problem still be there? Or is the problem because not everything is persistent?
Mm-hmm.
You're close because most of your memory is, so let's close the gap and then make
Yeah.
Everything is persistent, you mean the PC of the program you can actually, that's the question. If you assume that's a checkpoint, basically. Everything
I'm
is
asking
Yeah.
why is this issue new, so to speak? Because the need for checkpoints has been there all along.
That's right. Yes.
You only make life easier because most of the memory is persistent.
Uh-huh.
So the question is, why does that motivate?
Why is that unique to persistent?
So basically, so I think his question is very... If everything is persistent, this problem would not exist. You're right.
I don't agree.
You do not agree with this?
What do you mean by everything?
Basically, everything, all of your registers in the machine is persistent, right?
The program counter, everything.
Yeah, everything, sure. I think then the problem goes away, right?
What I'm trying to say is, I think this issue 20 years ago
Uh-huh.
was more severe because none of the memory was persistent. Now that you're assuming persistent memory, it makes life easier, but the need is still there. So, are you saying I'm going to try and, relative to old work on checkpoints,
Uh-huh.
I'm going to show how you can take advantage of the fact that most of your memory is now persistent
Uh-huh.
and make life easier, faster, lower overhead.
No, that's not what we're saying. No.
So what's
So basically, if you have volatile memory,
Yeah.
you don't have this problem, right? You crash, and everything goes away.
No,
You
but
restart from some point because you have not manipulated any persistent data. So let's assume that you have a program that requires some.
Okay, you turn it.
Okay.
Exactly. Exactly. So turn around and think of it that way. If you have volatile memory, you crash and you start from scratch, right? Because you haven't touched some persistent data that left you in some inconsistent state. So you could solve the problem with transactions, as I said. You could say, okay, this is my transaction, and if I crash somewhere in between, I always give you the illusion that I never crashed before entering the in between.
Put something in the disk. You have the same thing also.
You're saying that you're basically
Yeah.
saying in the old days, you knew you couldn't trust the memory.
Uh-huh.
If you cared about your data, you kept it on disk, a copy of whatever,
Uh-huh.
and if you wanted to occasionally checkpoint it, put it to update, so don't need to start from scratch.
Yes.
If you crash, you started from there.
Exactly. You start from there.
Now, you have the illusion that you have, you don't need that extra copy
Uh-huh.
because you have persistent data,
Uh-huh.
but now you have the new problem that you're changing the original
Exactly. Yes.
copy, so now it's
Exactly.
okay.
Exactly. Yeah. Exactly. So now we're on the same page. Yes.
So
Yeah.
unlike what was said in the problem statement before, in the past years, the programmer should have been part of the solution, or else nothing will stay persistent.
What do you mean in the past years?
I mean, before you had persistent memory accessible like you have today, if the programmer wouldn't have done anything, nothing would be persistent.
Well, programmer uses, let's say, file system I/O, right? That's how you do the persistence
No, but
today. So you do something, but it's very minimal.
sure, but then you said, okay, we need to add the programmer to the game. So no, the programmer would have been in the game to begin with, or else no persistence would have been used before persistent memory.
Okay.
Careful programmer would have had to write this checkpoint to
Yeah, assume there is no checkpointing though, right? So assume that you take a random application. So let's assume this case. You take a random application that you've written, and you run it, and everything is persistent right now. You touch an array, and that's persistent. So and the system crashes in between. What happens? Because you manipulated all of those data structures that are out there, and you're going to access them again, and there's a problem, right? Because you're starting from a completely inconsistent state.
There's also a question about the nature of crash. You said, okay, lack of power for 1 second, for example, but what if the operating system was crashed? Do you really want to go back from the place that really leads to the same crash?
Yeah, so I think those are some things that need to be thought about. Like you may have an application. If the application crashes, this works. If the operating system crashes, but we provide a full system checkpoint. So if it would work in that case also. Okay.
You remember the red?
Okay. Thank you, Ronnie, for reminding me of the rats. Okay. Basically, I think the programming ease to exploit persistence is really important. We can discuss this more, but I don't want to get into the rat hole. Okay, so we've also been looking at tools to help programmers to convert existing programs that are file system based to exploit persistent memory that are load store based. It's not as easy, especially if you want to do this automatic conversion automatically, because you need to figure out what needs to be persistent and what doesn't need to be persistent. And this doesn't really get completely explicitly specified today, but you can take a look at that paper. Okay, I'm going to skip this because I already said a lot of this over here. So we want to enable a new memory technology, and we've enabled memory technologies before. How do we enable new ones? Okay, any questions? No. I shouldn't have done that. So we're going to switch gears to a completely different topic. Oh, if we can. Let me see. Let me see if this is the right file, first of all. Ooh. Should I wait for you, Roma? Okay. So do you have more questions over there in terms of persistence? Okay, maybe we can take that offline. I think this is really interesting. But we are on the same page now? Okay, good. Okay, I think this takes some time to wrap your head around, in my opinion. It's not that easy concept, because if you're coming from one direction, then you may think that actually, oh, because checkpointing is for a different purpose here. It's not for fault tolerance. Okay, so we're going to switch gears. We're going to talk about something also fundamental, which is memory interference and quality of service. And as I said earlier, this problem is going to get worse in the future. And I'll start with shared resource design for multi-core systems. And as I showed you in the past, most of the memory system is a shared resource across different computational units. But I'll start with very basics, resource sharing versus resource partitioning. The concept of resource sharing is very simple. Instead of dedicating a hardware resource to a hardware context, allow multiple hardware contexts to use it. Example resources could be functional units, pipeline, caches, buses, memory, interconnects, and storage. Why do you want to do that? Basically to improve efficiency. Resource sharing improves utilization and efficiency. That leads to higher throughput because resources are not always utilized by a given thread or hardware context. When a resource is left idle by one hardware context, another hardware context can use it. And there's no need to replicate the shared data as well. This is another point over here. If you actually share the resources, then you don't need to replicate shared data across different contexts, right? And it also reduces communication latency. For example, if you have shared data kept in the same cache in simultaneous multi-threading processors, then you can communicate through that shared medium much faster, as opposed to going to some other partition to get the data. And this is compatible with the shared memory model as well. Again, if you're sharing data somehow in the shared memory model, having a shared resource that houses that shared data just makes sense, conceptual sense, right? So the disadvantage, of course, it leads to contention of resources, right? When the resource is not idle and another thread needs it, it cannot use it because it's not idle. And idleness actually happens in space and time. This is time-based. But if the space is occupied by another thread's data, one thread's data, another thread needs to reoccupy it. It cannot use it. Both threads cannot occupy with different data at the same time, if it's not shared data, of course. So this leads to a reduction of each thread's or some thread's performance, maybe the entire system's performance. And there are cases where entire system's performance reduces because of contention in shared resources. Imagine when you have two threads running, they both get perfect row buffer when they're running alone, they both get perfect row buffer locality. But if they contend for the same bank, they all get row buffer conflicts all the time. That could happen. As a result, thread performance can be worse than when it's run alone, and the entire system performance can be worse than when you have only one thread. And this eliminates performance isolation. As a result, you may get inconsistent performance across different runs of the same thread or workload. And the thread performance depends on co-executing threads. And I'm going to show you examples of this. And it leads to uncontrolled sharing. Uncontrolled sharing actually degrades quality of service, right? You cannot satisfy quality of service requirements. So you need some controlled sharing. Basically, this causes unfairness and starvation. So basically, there is a need to sharing resources is good for efficiency, but there is a need to do that in an efficient and fair way to utilize the shared resources. So basically, sharing improves throughput, better utilization of space and time. Partitioning provides performance isolation, predictable performance, because you get dedicated space. The key question is, can we get the benefits of both somehow without really giving up resource sharing? And the idea is to design the shared resources such that they're efficiently utilized, controllable, and partitionable. This leads to no wasted resource and hopefully quality of service mechanisms for threads. So to satisfy this idea, we would like to enable things like this. So this is an example, more concretely. Memory system, if you look at it, you could have a shared cache, shared memory controller, shared memory banks. And it's the major shared resource that we have today. So and threads request interfere inside this memory system, then how do you actually handle that interference? And it's going to be much more of a shared resource in the future. Even this is an old picture over here. Okay. So basically, what is the problem? The problem is threads today share the memory system, but the memory system usually doesn't distinguish between different threads requests. Now some sort of quality of service is added into the caches, for example, with Intel. ARM also has their own quality of service mechanisms. But beyond the caches, there is not a whole lot of very strong quality of service guarantees. So a lot of the existing memory systems, this is an old slide, a lot of the existing memory systems are free for all. They're shared based on demand. And the control algorithms we have are thread unaware and thread unfair. So as a result, aggressive threads can deny service to others. And the memory systems do not try to reduce or control inter-thread interference. So we can always do better to control and reduce inter-thread interference. So we're going to talk about some ideas. So when we first started looking at this, it was around 2006 or so, when I first joined Microsoft. Basically, we did the studies like this. This is actually a real result from Intel Pentium D at the time. I don't know if people remember Intel Pentium D. I think Ronnie probably remembers it very well. Basically, this is what happens if you run two applications together, MATLAB, GCC. Many of you may be familiar with them. We measured the slowdown each of these applications experiences compared to when the application runs alone on the same system. And MATLAB slowed down by 7% compared to when it's run alone, if it's run with GCC. And GCC slowed down by about 3x compared to when it's run alone, if it's run by MATLAB. Why? Because they're interfering in the shared resources somehow. And in this case, the Pentium D looked like this. Basically, it was one of the earliest, maybe the earliest multi-core processor from Intel. Basically, you had dedicated caches, some shared interconnect, and shared memory controller. And the reason we got this result was because there was unfairness in the memory controller. You actually could change the priorities and nothing matters because these are the two applications running in the system and the operating system doesn't deschedule applications based on priority. So what was happening? I'll take the liberty of calling MATLAB stream and GCC random, even though that's not a perfect characterization of this, because GCC is also actually not very intensive compared to MATLAB. But basically, one application is generating requests. The other application is also generating some requests. But the DRAM controller is prioritizing one application over the other, over and over. And as a result, that application is not slowing down that much, but the other application is slowing down a lot. And we actually tried to do this study in a controlled manner, and we wrote this application inspired by the stream workload that measures memory bandwidth. What this does is it copies one array to another over here, and it copies in a streaming manner. And we ensure that every access is a cache miss in this case, so it's very memory intensive, as you can see. It has sequential memory access, and we measured the row buffer locality to be very high. And the other application, we wanted to control this study. We wanted to have similar memory intensity. Essentially, it does the same thing, copies one array to another, but not in a sequential manner, in a more random access manner. So the indices that you access are random accessed. And of course, you don't write the program this way, because if you actually have this random number generation inside the for loop over here, then that takes most of the time. So you generate your indices earlier and then hard code those accesses. As a result, you can emulate the random access. So you really want to equalize the time that you measure over here. Okay, so this is random memory access, similarly memory intensive, and very low row buffer locality that you get over here. So what is the memory hog? We call this the memory hog, basically, at that time. Actually, memory hog is MATLAB also. MATLAB looks kind of like this when it's streaming. GCC doesn't look like this because GCC is not very memory intensive, and that actually makes it worse a little bit. So what does the memory hog do? Remember this picture over here? That's the bank that we have. The memory hog is accessing the same row over and over. It's similarly memory intensive. So what's happening is the memory controller sees the memory hog accessing something in the open row. As a result, it prioritizes the requests of the stream application, the memory hog, right? Because the random access application is not accessing a row that's already in the row buffer. As you can see, the memory controller always prioritizes the requests that hit in the row buffer. And as a result, it implicitly prioritizes the memory hog, which is stream in this case. Yes?
But there's actually a very smart thing in doing this, because if you look at the total memory time taken to satisfy any request from here and
That's right. That's right, yes.
Had you done it fair, you would have screwed both of them.
Not necessarily both of them, right? It would increase your average memory access latency, that's true, but it will help this red one. Right? Red one will not slow down as much.
Yeah, but would have hurt the blue one.
It would hurt the blue one, yes. Compared to what it's the baseline that you start with, it would hurt it.
Depending on the ratio of roll hit time to roll list time,
Mhm.
mainly the DRAM, this could go to mostly screwing the MATLAB without helping the other one much.
Well, in this case, I think it would help the red one a lot, actually. Because in this case, red one's starved, right? So red one is not getting any request service until the blue one stops accessing row 0.
Yeah, but let's say it's 10 to 1 latency between hit and miss.
Oh, it's not 10 to 1. It's about 2 to 3x. Yeah. Yes.
And how many log spaces, cache lines per row?
Yeah, let's say 128 cache lines. Right. Basically, with these assumptions, with a row size of 8 kilobytes and a cache block size of 64, you have 128 requests of T0, which is stream service before a single request of random access application. Yeah. And this is just one example of the unfairness, basically. You starve an application, and this is one instance, basically, because you're exploiting the row buffer locality over here. So why is this happening? Basically, a row conflict memory access takes significantly longer than a row hit access, 2 to 3x. And current controllers, at the time at least, take advantage of the row buffer. The commonly used scheduling policy, as we discussed earlier, is you prioritize row hits over others, and you prioritize older access over others. This scheduling policy aims to maximize DRAM throughput. As we said, this is not a bad policy, but you can do better with reinforcement learning-based memory controllers. But it is unfair when multiple threads share the DRAM system. If your goal is to optimize DRAM throughput, this is not bad. But if multiple applications are accessing the DRAM at the same time, your goal may not be to optimize DRAM throughput, but because if you're optimizing DRAM throughput, you're implicitly prioritizing things that make better use of that DRAM throughput. So this is actually, again, same. We also did the study on Pentium D. You see that stream slows down by about 18% when it's run with random, and random slows down by about 2.8x. That's true for Stream and GCC, and this used to be Microsoft's virtual machine at the time. I don't know if it exists anymore. But yeah, you can see that this Stream is denying service to many things, and we called it the memory performance hog, and you can read this paper that talks about this as an attack that you could do. Okay, so this becomes a more general problem with more cores. This is simulated data, basically 4 cores over here. LibQuantum, it's a quantum computing simulator that looks very much like Stream. It basically slows down by 5% over here. And if you're running some other application, it slows down by 8x over here. So basically, this issue opens up a vulnerability to denial of service that gets denied service for a while. You're unable to enforce priorities or service level agreements. Basically, you may actually care about this video encoder or decoder, right, that has some quality of service requirement, but you cannot enforce that quality of service. And this also leads to low system performance because what happens is it turns out the memory-intensive workloads implicitly get prioritized over memory non-intensive ones. So this application, if you look at the application level, this application generates a lot of requests to memory, and memory system implicitly prioritizes it. This application generates requests once in a while, but it gets queued behind this application's request because of the oldest first part of the scheduling policy. And as a result, this waits for a long time. Even though if you did the exact opposite thing, if you gave up throughput in this application just a little bit and prioritized this one just for that request, you would enable this to make progress in its cores because it's going to make a lot of progress in its cores until it gets to the next memory access. That way, you can get much better system utilization overall. So the system optimizing for data throughput is not necessarily good for overall system performance. So that's also true. Basically, you have.
How do you define in this case overall system performance? I think that's the question.
Yes. So assuming equal priority applications, it's weighted speed up, let's say. Weighted speed up is really the sum of slowdowns.
So that's the definition, or instead of
Yeah, time to complete all of them could be another one, right? In this case, you delay this one a lot, right? Yeah. Okay. Or you could define it in a throughput metric, right? Okay, but this is a general problem with more cores. You see all of these effects. So whenever you run different applications, you get these unpredictable performance. But if you did something else with scheduling, you could do much better. So we've actually looked at things like on-chip networks also. If you have cores connected via packet switch routers on a chip, you could run into these really bad contention cases. For example, you have a memory controller over here, and you have an application that may naturally or maliciously be targeting this memory controller. It could happen naturally also. And if you have some sort of routing that's fixed that doesn't take into account quality of service, this is XY routing, for example, dimension order routing, the requests basically keep going this way. And as a result, some other application that's trying to access this memory controller will get denied service. And we actually provide quality of service mechanisms, which we may talk about, but we're probably not going to get into that. So you get actually significant latency increase, especially with large-scale systems over here. So it's not just the memory controller, but it's all of the scheduling mechanisms that you do. Any kind of interference can lead to this sort of denial of service. So this is the paper that I've been showing data from, and this is the other paper. So basically, that's the motivation. We have inter-thread interference, and it's uncontrolled in all memory. Memory controller interconnect caches. And at the time we started, caches didn't have actually control. There was work that was published around 2004, 2005 or so. Ravi Iyer, for example, did some work that had quality of service in the caches. And now I think it's in products, finally. But it's not clear if that's true for the memory controller or the interconnect. So how do you solve the problem? You need to control it. Basically, we need to design an interference-aware or quality of service-aware memory system. And I think there are three questions over here. First is, we would like to reduce inter-thread interference as much as possible, because that improves overall performance. If you can reduce it, that's great. This improves system performance and core utilization. It can reduce request serialization and core starvation. Next, you would like to control it also, basically provide mechanisms to enable system software to enforce quality of service policies while providing high system performance. So if an application is really critical, one way of actually ensuring that it gets its performance is to ensure that nothing else runs together with this application. But that's a terrible solution, because then you don't get high system performance, right, overall. And the next one is, how do we make the memory system configurable and flexible? Basically, we don't... There's no single quality of service policy that works for every system, every point in time, and every application. So we need to be able to have flexible mechanisms that can achieve many goals. Sometimes you care about fairness, sometimes you care about throughput, sometimes you care about latency, sometimes bandwidth, sometimes some slowdown requirements. So you want to satisfy those different requirements. And this makes it a little bit harder, of course. Like if you have a hardware accelerator, it has some bandwidth or latency requirement. If you have GPU, it has some bandwidth or latency requirement. If you have a particular application that interacts with the user, it has some latency requirement, probably. How do you actually have the memory system satisfy all of those different goals at the same time? So I'm going to talk about several approaches to this. I think there are two high-level approaches. One is, you can design your resources to be smart, as opposed to optimizing for data throughput, for example, as they are usually designed, memory controllers. They could be optimized to have some quality of service control and reduction, interference control and reduction mechanism. I call this quality of service. There are memory controllers, interconnects, and caches. We're going to cover memory controllers a lot over here, because I think this is the more ignored part of the system, although interconnects, at least within the on-chip context, is a little bit ignored also. I think there's a lot of work on caches. People realize that quickly. After all, it's the International Symposium on Cache Architecture, right? That's, as you know. You can read the cache papers on your own. And the second approach is also very interesting, I think. I call this the dumb resources. And this is to show these are not necessarily incompatible with each other. But you can keep each resource free for all, but reduce and control interference by doing injection control or data mapping. Basically, you can keep your memory controller as is, but what you do is you throttle the access rate of different cores inside the memory system. So if you think of your memory system as a shared resource, I'll call this memory. And you have different cores that are injecting stuff into it. You keep this as is, but you basically identify the problems that you're having in terms of fairness or unfairness, or whether or not you're satisfying the requirements, and basically control the injection at the periphery into the memory system. It's kind of like how the internet works right today. But that's not the only way. This is called source throttling. But you could also do intelligent data mapping. That's quality of service aware in the memory controller. You can try to exploit the fact that you have different channels in memory, and you can partition the applications to different channels. You can partition the applications to different banks such that they don't have the sort of interference that we've seen before. Or you can have quality of service aware thread scheduling to different cores. And we're going to cover some of these mechanisms over here. And in the end, these are, even though I show them as completely separate solutions, you can combine them, right? You can do both, right? You can have a quality of service aware memory controller, and you can still control injection into your memory system such that you can get the best of both worlds. So we're going to focus a lot into the memory controller part because we've been working on it for a long time. As I said, it's more ignored. But let's talk about the fundamental techniques. I think there are 4 fundamental techniques. The goal is to reduce and control inter-thread memory interference. One is prioritization or request scheduling, right? And this is true for any part of memory system. You could do this at the caches, memory controllers, interconnect. You have some sort of prioritization or request scheduling policy. And you can make that quality of service aware. The second is data mapping to some sort of place, that banks, channels, and ranks. This is space partitioning. This is employed heavily in caches, for example, today. You are able to control the data mapping to different parts of the cache, either in software using page coloring. You could do that actually. When we didn't have the quality of service aware caches, you could partition the cache between different applications using page coloring, right? That's one way of data mapping. You could do the page coloring in the memory channel also. Next one is core or source throttling. That's another approach. These are all different approaches, as you can see. And the last one is scheduling of the thread and application to a particular core. Because if you actually do the scheduling right, maybe deschedule some of the applications at the right points, you may actually get higher performance and satisfy the quality of service requirements. So we're going to cover a lot of this to begin with, but then we're going to look at examples of this after this prioritization part. Does that sound good? I see people are getting tired. Okay, maybe no. I hear no also. Okay, so basically, what is the prioritization? As I said, we're going to focus on memory control, but it's a similar issue exists in caches. The problem, of course, it's bigger in memory controller because the latencies are much higher over here. So a memory controller, one of the functions of the memory controller is to resolve memory contention by scheduling requests. The key question that we're going to ask is, how do you schedule the request to provide high system performance, high fairness to applications, and configurable to system software such that you can prioritize some applications over the others? And I think there's no question that the memory controller needs to be aware of threads in some way. Explicit awareness is a good idea, but maybe you can implicitly also discover that these requests are coming from this thread or this other thread. I think explicit awareness is the best solution, basically. With a request, you say, oh, this is coming from this hardware context at this point. I'll give you the evolution of this. I'm not going to talk. Maybe that's not a good idea. OK. These are some slides that we may get back to later on. So this is basically very quick summaries of every single idea that we've looked at. And you can take a look at it after we cover some of the ideas, because we're not going to cover all of these ideas. I just put the key takeaways over here, and some of them. Is it enough? I don't think that's enough, actually. There's more to be done, right? Frankly, there's more to be done. But we've moved on also. We're not looking as much into this direction at this point. But I think it's really interesting. So the first solution that we came up with after we saw that memory performance attacks is, why don't we be fair? So this is the unfairness problem, right? You see slowdowns are very disparate from each other. And now fairness is always very contentious, right? How do you define fairness is a problem in systems in general, in life also in general. We're going to use some definition of fairness. So the idea we developed was this, total time fair memory scheduling. The goal is to have threads sharing the main memory experience similar slowdowns compared to when they run alone. And that was our definition of fairness. The hope is that if you actually do that, if you have similar slowdowns, this also improves overall system performance, the hope. It's not always true, by ensuring cores make proportional progress to each other. Everybody's equally slowed down. So the idea, it's not an easy idea to implement. The memory controller estimates each thread's slowdown due to interference and schedules requests in a way to balance the slowdowns. Now, how do you do that estimation? That's the difficult part. Let's go into that a little bit. So basically, we defined a DRAM system to be fair if it equalizes the slowdown of equal priority threads. We're going to assume everything's equal priority, relative to when each thread is run alone on the same system. So we define DRAM-related stall time as the time a thread spends waiting for DRAM memory, how much it is stalled. And stall time shared is the DRAM-related stall time when the thread runs together with other threads. And stall time alone is DRAM-related stall time when the thread runs alone. So hopefully, stall time alone is something that's lower than stall time shared, right? And the memory slowdown is defined as the ratio of these two stall times. Stall time shared divided by stall time alone. This is relatively increase in stall time. For example, when you're running alone, you wait for memory for 1 millisecond. And when you're in together with some other thread, you wait for memory for 5 milliseconds. Your slowdown is 5. And some other threads may wait for 1 milliseconds when it's running alone. Another thread, and it may slow down by, it may wait for memory 10 milliseconds when it's running on. It's slowed down by 10, right? So 5 and 10 is a disparity, so we want both of them to be equally slowed down. You could argue that this is not a good metric, right? May or may not be good, but the results are not bad. Okay, so the idea of the stall time for a memory schedule is to equalize this memory slowdown for interfering threads without sacrificing performance. And this considers the inherent DRAM performance of each thread by taking into account the stall time alone. And the aim is to allow proportional progress or proportional slowdown of the threads. So how do you do this? Assuming that this is a good thing to do, which may or may not be good, we're going to improve on this. How do you actually implement this? So for each thread, the memory controller tracks the stall time shared and estimates stall time alone. So tracking stall time shared is actually easy. You basically count how much time do you stall waiting for main memory when you're running together with other threads, and communicate this to the memory controller in the core. You could do that. This is the hard part. How do you estimate stall time alone, right? Because you're running together with other threads, and you want to figure out what would your memory stall time have been if you were running alone. You don't want to deschedule all of the threads to figure out what would your memory stall time have been, right? So we actually have estimation mechanisms that try to mimic this. For example, I don't have this actually over here. Okay, maybe I will not have this. So basically, what we try to do is stall time shared for a given thread. Stall time alone is essentially stall time shared minus some excess waiting time, right? So basically, stall time shared, you get to stall time shared because you have some excess latency. So we want to estimate that excess latency. So when does that excess latency happen? In the memory controller, when you schedule a thread's request, you know what you're delaying also, or you can easily figure out. If you schedule thread 0's request, you know that you're delaying thread 1. So you know that you're slowing down that thread 1. So you can have a counter that basically says, oh, I'm adding an excess stall time for this particular thread by this amount. So it's basically accounting by how many cycles do you actually delay a particular thread because of contention coming from some other thread. Of course, this is not really easy to do because, yes, when you actually cannot schedule a request because some other thread is using that bank, you know that you're delaying that thread's request. Okay, but what about the row buffer, right? The row buffer actually changes also. So we actually introduced shadow row buffers to guess which row buffer would have been open if this thread was running alone in the system. So that adds overhead. But what about the parallelism of the request? Because Well, in this case, we simulated what we thought could be implementable.
You want to implement a shadow row buffer.
Exactly, yeah. Well, we don't keep the data in the row buffer. We keep what? Exactly, the address, basically. You have shadow tags, if you will. Which row would have been open if this thread was running alone in the system? Of course, it's not perfect, right? You cannot get this perfectly right. Because if you want to get it perfectly right, you should really be running a memory controller that's dedicated to this thread, and that's not easy to do. But we have estimates of this. The most difficult part of this is, yes, you can guess what the shadow row buffer is. You can guess what the delay is. Well, there are two most difficult parts. I think one is writes and reads. Now, writes and reads get mixed in the memory controller from different applications, and that's very hard to determine when you do the write and read scheduling. So it's very difficult to figure out what your stall time alone would have been, because you don't have an idea of when your writes would have been scheduled if you're running alone. And the second part is the parallelism. Basically, when you actually you have requests interfering from different applications, that destroys the parallelism that you have in a single thread. So you may actually say, okay, this request is delayed by this much, but this thread also has some other request, and that may also be delayed by some other amount. But that latency would have been overlapped if you were running alone, right? And it's very difficult to figure out how much of your latencies would have been overlapped when you're running alone, because that affects your stall time. So this is the difficulty of it. So I think this is not an implementable mechanism, but this was a conceptual way so that we could move forward. But we did actually implement the simulation as best as we can. It's not perfect, of course. We don't take into account all of the factors. So assuming that you can guess the stall time alone with these approximations, the memory controller computes a slowdown, stall time shared divided by stall time alone, for threads that have legal requests that can be scheduled at that point in time. And it computes an unfairness value. Unfairness value is the maximum slowdown in the system for any thread divided by the minimum slowdown in the system for any given thread at that point in time. And then it checks, basically. If unfairness is less than some system software specified threshold, it uses a DRAM throughput-oriented scheduling policy. So things are going well. We're not extremely unfair, so maximize DRAM throughput. If we are unfair beyond some alpha, which may be specified by the system software, then the memory controller switches to the fairness-oriented scheduling policy. Basically, it prioritizes the request from the thread that is experiencing the highest slowdown at that point in time. And if there are no such requests, you prioritize row hit first and oldest first. So that's the idea, basically. You switch between two policies. One is fairness-oriented and the throughput-oriented, based on the unfairness that you think is happening in the system. I will simulate this with the same example over here. So basically, if you have two threads, the memory controller needs to keep track of the slowdowns of the thread and the unfairness, which is the division of these. And let's assume that we have an alpha of 1.05. That's the tolerance, maximum tolerable unfairness that we have in the system. And we'll start with a streaming application. In this case, that request gets scheduled. It doesn't delay anything, so nothing changes. In this case, if you look over here, both of them are slowed down by 1.00. Here, thread 0's request gets scheduled because we're using the throughput-oriented scheduling policy because unfairness is still tolerable. Thread 0's request gets scheduled, and what you do over here is increase thread 1's slowdown because you've delayed it by some amount. And you know exactly by what amount you delayed it, at least in this bank. The problem happens if you have many banks and many channels, right? Now your parallelism also gets destroyed. Okay. So unfairness is still tolerable. So we're going to keep using the throughput-oriented scheduling policy. And we're going to exploit the row buffer locality here. And after this request gets scheduled, the memory controller figures out that the slowdown is 1.06 over here. And unfairness is greater than the threshold, which means that after this request is done, the memory controller is going to prioritize thread 1. It's going to switch to the fairness-oriented scheduling policy, as opposed to the baseline where it would prioritize this one. And it switches to the fairness-oriented scheduling policy. Now row 16 is open over here. And both threads, the thread 0 slows down over here, as you can see. Right. Now unfairness is back in check. We can switch back to the throughput-oriented scheduling policy, and none of the requests are to the row buffer that's open, which means that we pick the oldest one. Now, once we pick the oldest one, because of the shadow row buffers, we realized that, oh, this would have been a row hit if it were running alone. We open it. So both of the threads slowdown actually increases because we're delaying this one because of interference. But this one is also slowed down because we realize that the request is to row 0. And if this thread was running alone, row 0 would have been open because you have a shadow row buffer or shadow tag row buffer addresses. So both threads slow down. This one slowed down more. As a result, unfairness is like this, but it's still in check, which means that we can keep exploiting row buffer locality a little bit more. And that's what happens. Now unfairness is back out of control. So you switch back to the fairness-oriented scheduling policy. And unfairness is back in check. As you can see, you keep switching back and forth between fairness-oriented and throughput-oriented scheduling policy to keep the unfairness in check. And that leads to a better system throughput because this thread exploits row buffer locality somewhat because of this selection of alpha. But this thread can also get its request serviced. As opposed to this core starving, now both cores can make progress. Question? OK, so that's the idea here. Of course, the complexity is not easy. So the upsides over here is this is really the first algorithm that takes into account all of the issues related to the DRAM subsystem. There were previous algorithms in multi-core systems that basically applied network fair queuing into DRAM. We actually compared to those algorithms in the paper. I don't think those are actually a good fit for DRAM because DRAM has banks, which is not present in a router. And DRAM has row buffer locality, which is really important in a router. So as a result, those algorithms don't scale really well. Sometimes that's good. First come, first serve is more fair than network fair queuing. And it provides a mechanism to estimate memory slowdown of a thread. I think we're going to get back to that. I think this is actually really important. If you can estimate the slowdown of a thread, that's great. But if you do it in a very fine-grained manner like we do over here, it's actually very difficult and very complex to estimate. So we're going to get back to this, and we're going to try to use higher-level insights like request service rate and how much you're changing your request service rate to estimate the slowdown of a thread later on. So I think estimating the goal of the paper is actually good, in my opinion. You want to estimate the slowdown of a thread because that gives you how much you're slowing down something. But the implementation is not very good, I think. So it's good at providing fairness. And being fair can improve performance. And that's shown in the paper also. The downside is this doesn't handle all types of interference, which I'm going to talk about. And it's complex to implement. Maybe you can remove that somehow over here, somewhat over here. Slowdown estimations are actually very incorrect. But it gets you the ballpark. Which one should you prioritize? That's what you really need over here. We're not using the slowdown estimations for some other purpose. OK, so if you're interested, this is the paper. And we were naive at the time when we wrote it. But this enabled us to discover many, many things. So let me go on to the next one. Any questions on this? Yes?
Yes. How well did it eventually?
I see. I don't have the results over here.
I mean, in retrospect, you can check it. I mean, you run here.
Yeah.
You run in one way. You run them alone. You run them and you know.
Yeah. So it actually improved system performance. It actually improved fairness significantly. I'm going to show you the results at the end of this next one.
Okay.
Yeah. I don't want to show the results because then I would show results for every single one. It becomes very boring. But at the end of this one, I'll show you the results of multiple mechanisms. But it did improve performance and fairness, both of them. Yes?
Isn't there a risk of running into a constant unfair condition where you choose only the order, you only dispatch requests because of the order, and then you lost locality? I mean, what I'm actually trying to say is, if you choose the unfair or the unfair strategy, does it guarantee you to get back to the fair situation of the system?
Well,
You also consider the slowdown in that condition, right?
Mhm.
So unfairness may still
Yeah.
go up in this condition.
So if you prioritize the thing that has been slowed down the most, assuming your estimations are correct, then I don't think you would run into that situation. But it of course depends on this alpha, right? If you choose that alpha to be extremely tight, if you say 1.00, then yeah, it's not. Actually, we show that if you choose 1.00, that's not a good choice. You don't satisfy it, first of all, but also you lose a lot of performance because you don't exploit robot for locality very well. You need to choose your alpha nicely.
But the risk that I see here is that while you are in the unfair or trying to fix the wall, you're also experiencing unfair treatment of the other thread. So the parameter may still rise. The unfairness parameter may still rise.
Yes, that's right, but it's you go back and forth in the end, right?
I'm not sure. Is it guaranteed to cross back to fair condition?
I think it depends on the choice of alpha. I will go back to that. If your choice of alpha is, let's say, 2. Yeah, so exactly. I think that's a good question. We actually look at that, and there are some alphas that you can never satisfy. But there is an alpha that exists that you can satisfy. The question is, how do you choose that alpha? That I don't know for sure, right? If you always look at that alpha as very loose, for example, if you say 10, then you can satisfy that. Yeah, exactly. You may gain nothing also. So, but there is an alpha over there that I believe satisfies what you said, but we don't know how to find that alpha. Yes?
Suppose there were no issue of locality, of zone locality.
Yeah.
So an axis is an axis is an axis.
Mm-hmm.
Would there be a simple policy then?
Yeah, I'm not sure. So there's robot for locality, but there's also bank level parallelism. The paper goes into a lot of detail into those two. And that's what makes DRAM very different from a network router. There's locality and parallelism. So you really need to have a single server queue for all of the theory in scheduling to apply here. If you have a single server queue with no locality, no bank level parallelism, now scheduling theory is great. But here you have multiple servers, different banks, plus locality, plus there's an application running. It's not just a flow that keeps going, right?
I raise this for a different reason. That is that your approach is to try and estimate the penalty, delay, and balance that. Another would be knowing the penalty of not exploiting the locality.
I see.
Exploiting locality has diminishing return.
Mm-hmm.
In other words, if I give a burst of 4 requests, that gets me most of the benefit.
Mm-hmm.
Even if I then swap those, etc. And then what you could do is simply say when you give priority to the bursts, but only up to a certain length.
Yes.
That's very easy to measure locally and
Mm-hmm.
view, just for the currently active row.
Mm-hmm.
And just limit burst length.
Yeah.
The rest use some kind of line of burst not per serve, rotating.
Yeah.
But for the multi-bank,
Exactly. Multi-bank is not easy. Yeah, actually, in this paper, I didn't talk about it in detail, but we also introduced something like what you suggest. We call it FRFCFS cap. Basically, you cap the number of reorderings that you do compared to. So you basically limit how much you're exploiting robot for locality in lieu of some other application. And that actually is more fair than FRCFS for sure. And you could actually improve upon that. I'll get back to some more simpler solutions later on. This was a more complex solution that we designed. But again, I think in the end, even though the papers show evaluation, maybe one algorithm is better, it's really workload dependent. This FRCFS cap is actually a good policy. We later discovered that AMD controllers were doing that apparently. They're capping the number of reorderings. But it's not, it doesn't solve all the problems, but the bank level parallelism and intensity also. Okay, should we cover the next one or should we call it a day? Go ahead. Okay, I hear go ahead. But say it again. How long is that? That I cannot estimate. So if we cover the next one, you got, oh, this is transactional. We got to go until the end. What do you think? Let's finish. Okay, we're going to do a vote here. Maybe I can finish in 10 minutes, but it's going to be not so easy.
tell them it doesn't change the content of the exam, the scope.
I see. So I'll take a vote. Who wants to go ahead? Who wants to stop here and ask questions? Okay, then you got to ask questions if you want to stop here. Okay, more questions because this is going to be a fun. Actually, this is a paper that I'm going to assign. I think I love this paper more than the previous one. Definitely tomorrow. I see. So more questions. Yes. I see people are tired. That's why I don't want to necessarily go. Yes, there's a question.
Sorry to mention, but during the previous chapter, you started with referring to threads, and then you moved to code, and then you came back to.
Yeah.
The remote controller is not aware of threads.
Yeah. So basically, I was very loose. Basically, I was assuming that you're really talking about hardware contexts. So whatever is generating requests, you basically identify which hardware context is generating those requests. Today, memory controllers are not aware of that. And maybe they're aware of that right now, but at that time, they were not aware of that, basically. So you need to, with each request, you need to tag each request with the hardware context ID. This is not the software thread. There could be a benefit of doing that also, but we didn't explore that. What else? Otherwise, I'll start covering.
Did you take into account in the previous article?
This one?
Yeah, the effect on context switching. Because if you're, let's say, more fair and you don't give a stream of memory to a single thread, it could context switch more often, which in return overall will negatively affect performance.
Yeah, so we didn't really take into account the fairness that we're targeting is actually much finer time scale than the context switching. So we're looking at, for example, in the order of 100 million instructions or so.
So you start it every time, or how? I mean, the system is live. It's not like you start 4 and then it ends.
Yeah, sure.
It runs all the time.
Sure.
So how, as opposed to simulation, how you envision in a real system that when you will start to count the slowdown?
Basically, whenever you start a thread, you can start counting it, right? So there needs to be some communication for sure.
Will have its own slowdown.
Exactly. Each thread has its own slowdown counter in the memory controller.
It starts when it starts.
Exactly. It starts when it starts.
And how can you check whether you are not in the situation that, I mean, maybe you're better off just let's say, serving one less thread than really start to do them all?
Yeah. So I think that's a solution we did not examine, basically, like descheduling the threads, right? Yeah, I think that's a very good solution, actually, throttling, completely not generating requests from a thread or completely descheduling a thread.
When you get into trashing each other.
Exactly, yeah. So I think, I think there needs to be more solutions developed in that direction. And if you're overloaded, it's better to throttle. And we're going to talk about source throttling. But we didn't examine that in this case. In this case, we assume that things are injecting requests at the rate they're injecting requests in the real application.
Since you asked for a question, I would like to...
Okay, sure. But you're also not taking the course. What about the students who are taking the course? Ronnie is a very good student, so. There's another question over here. Maybe we'll context switch. Okay.
Give it some slot of time.
Yeah, sure. Some fairness. Yes, please.
When you simulate that, did you just simulate two threads, like one streaming and one random? Because code processor has many threads.
No.
Several of them can have streams.
Yeah.
And once you get into a situation when many threads with streams oriented are violating the alpha, then you will get context switch between them all the time, and they won't be streams anymore.
Yeah. So no. I mean, that was just an example to motivate. Basically, we simulated a lot of real workloads, meaning multi-program spec at the time. And I think there were a lot of mixes, actually, maybe 100, 150 or so. So we did a bunch of large-scale studies. So we did simulate real application behavior. And as I said, if your choice of alpha is 1.00, that's exactly what happens. You break a lot of the locality that you have in the RoBuffer, and everything may look kind of randomish, right? Or at least you don't exploit the RoBuffer locality, and you lose actual system performance in that case, right? Because you're not utilizing the RoBuffer for any thread, even though all of them may be streaming. Because you're very strict in your unfairness, you're losing performance. So alpha 1.00 is not good. I think our solution, the best alpha empirically for us was about 1.1. But yeah, to answer your question, it was real applications. Okay, what else? Students who are taking the course, they can wake up. We still have 2.5 minutes. Otherwise, Ronnie can ask. Experts, yeah. Now they'll pay more attention to this tomorrow morning, because there might be a question coming from this on the exam, right? That's this is one of my favorite papers. No bias here. No other questions? Okay. Okay. So let's leave it the rest for tomorrow then. Yeah, see you tomorrow.